Hello everyone, it's great to see such a big turnout here. So my name is Anil Madhavapeddy. I'm a prof in the Cambridge Computer Lab. In fact, it's great to see Sebastian lecture. He used to be one of our students just a few years ago. And these days I work at a company called Docker. So I wanted to tell you about how we're using functional programming in a major product that we've been shipping for the last few months. Just before I start, how many people here have heard of Docker or used Docker? Well, that was awesome. How many of you have heard of OCaml? Actually, all of you now, hopefully after Seb's talk. A very quick introduction to Docker is that it's a bit of technology that has been transforming the development landscape. So it's been driving the move from big monolithic services to building small little microservices that are independent, specialized components and API endpoints that can be composed together as part of a distributed system. So it's really driven the move to the cloud. It's driven the shift to building bespoke services that just do one thing and do it well, and then letting the components individually scale up. So given that most of you have used Docker, I'm going to try to make this a fairly demo-intensive talk and just show you some of the bits and pieces from how this stuff fits together. Now, one of the things about Docker is the growth has been tremendous. So I joined towards the end of last year. And there's been this kind of exponential curve of usage in Docker where a lot of people just try it very quickly for a simple task, realize it's quite easy to use, it increases their productivity quite a lot, and then they publish and share their information on the Docker Hub. So this represents the number of pulls in the Docker Hub. It crossed 2 billion a few months ago. It's above 3 billion now. The curve continues to go up and to the right. So when I joined, we had a bit of a problem. So I'm an operating systems hacker who occasionally dabbles in functional programming. And I work on something called unikernels, which is trying to rebuild system software using safe technologies such as OCaml, functional programming, verification, to try to rebuild the way that we think about system software. So when I joined Docker, there's this insane growth happening in the back end. And the way that most developers consume the software is by something called the Docker Toolbox. So of all of you that use Docker, how many of you have used the Toolbox on a Mac or Windows to consume it? Interesting. So the majority of you have actually probably been SSHing into a Linux service and trying to use it there. But if you look at developers, what happens is that you're building a Linux container and you're deploying it, you're trying to develop using this Linux container, but in fact you're working on a foreign operating system. You're actually working on a Mac or a Windows desktop because the year of the Linux desktop hasn't quite arrived yet. So, and the way this worked is that Docker did the obvious thing. So in order to let the majority of the developers use the software, built something called the Docker Toolbox. And this is a loose kind of collection of all of the bits and pieces you needed to run Docker. So a full hypervisor called VirtualBox, which can virtualize an entire operating system. And then a little virtual machine that is designed to do nothing but run Docker. It's a Linux virtual machine. And then a UI that connected to VirtualBox and did all the things. But the problem is when there's a blast of users, a million developers download the Docker Toolbox, and you realize just how messed up laptops are, basically. Because the fact that these components are not very well integrated led to a huge flood of bug reports. Someone has problems with VirtualBox, someone has problems with the connection of these things, battery life is destroyed, and developers were losing that really nice dopamine rush of using Docker, deploying a service, and just having a good time using it, because the desktop experience was just not very good. So we thought, well, that's a fun challenge. So what can we do using our systems programming skills to try to build the most integrated app possible? So if you're building something for these millions of developers and we want them to develop using their native environments, is it possible to get computation to become universal? So no matter where this container was built for, if it's built for Linux or built for Windows, it should be able to run as close to natively as possible on a foreign host. So this container should be able to just be translated and run on Windows, run on the Mac, or run on Linux, eventually run on iOS, just run anywhere. So can we build an architecture that would support this as efficiently as possible? And to do this, we wanted to build, for example, start with a Mac app. So that's what it'll focus on. And this Mac app should be super easy, easy drag and drop, secure sandbox installation, so you don't need to have root privileges to run a container. This should be something that runs in Userspace, and just generally work with the native Mac networking and so on. So any local configuration changes you make would be preserved, and also try to make file systems just work. So the Mac file system is different from the Linux file system, so can we just make all this invisible? And we use a ton of OCaml code, and I'll show you through that to do all of this kind of translation. So first of all, to give you an idea of how this works, we're doing something a little bit unusual with functional programming. This is not a Monad tutorial, for example. We wanted to hide all of the functional programming, and no one should ever know that any of this stuff ever exists. All the users see is they drag and drop in a bit of Mac software. They put an invite code in. It's in private beta at the moment. It'll be in open beta quite soon. And once they drag and drop this bit of software, everything they need to run Docker is just available magically. So they don't need to do anything else. Auto updates are available and so on and so forth. You just have to type in your password as a one-off to instantiate it, and even that is disappearing. So that's it, right? No crazy installers or anything. So to pull this off, we needed to build a new way of doing virtualization. And the problem with existing virtualization is that it's very heavyweight. It was designed for a world where you build virtual machines that run in the cloud. They have gigabytes of memory, and they're big units of management, right? So you spin up these things on Amazon or on Rackspace, and the Zen tool stacks and the VMware tool stacks are not designed for lightweight, low latency deployment within a desktop. So we decided, let's not try to squeeze there at all. And let's actually build a brand new hypervisor that offers a new way of doing virtualization. So we took some open source components, known as Xhive and from FreeBSD, and we built a hypervisor that was the bottom half of the existing ways to do virtualization. So there's two bits of virtualization these days. The first one is the high-level management tool stacks and so on that you interact with when you use the cloud. And then there's the low-level stuff which maintains the actual isolation between all the various components. So we throw away all the management stuff, all of the stuff that requires gigabytes of memory. And it turns out that OS X and increasingly operating systems have support for the low-level stuff as part of their kernel distributions. So a lot of what made hypervisors special about 10 years ago is no longer interesting or unique. It's just supplied by the OS. So in OS X, we have something called the hypervisor framework, and this is supplied as of macOS 10.10, and it gives you all the low-level atoms required. So using this, it turns out that we could just take an unmodified OS X kernel, and without having any patches and so on, we could actually just run a basic hypervisor. And what the OS X kernel does is that it exposes just the atoms you need to do isolation of a virtual machine, paging support, the ability to take different parts of memory and to deal with traps and that kind of stuff. Then everything else, after this basic atom of hardware is exposed, is dealt with as a normal process in Userspace. So in Userspace, we run a normal OS X Userspace, and things like threading and I/O traps and ACPI power management are all just callbacks inside this process. Just like if you're building a Node.js app and you're building callbacks, or you have a monadic concurrency framework, there's that word, you can just express these as callbacks within a process. So it's just like a high-level application stack, except this is dealing with super low-level components in an OS. So we built all of this, but in such a way that it's designed only to run one thing. It's only designed to run a process that will eventually run Docker. And so this is the leanest possible way to do virtualization, and it's leaner by, in some cases, by orders of magnitude, because all it is running a normal Mac application. So inside our process, we then build a few very simple functional abstractions, and then we managed to get Docker. We managed to get a 5 megabyte Linux distribution based on Alpine Linux, and everything else around this is redirected back to the host. So your logs and so on are all provided by the host. This is just the minimum possible shell to make it all work. And part of the magic, and the reason we're talking about this at a functional programming meetup, is that all of these pieces in the scaffolding were largely written in OCaml. So if I escape from the presentation for a second, I have a little whale icon. Can you see the whale icon? That's it. That's what the Docker app is. It's running. I can restart it. If I look at the acknowledgements, where's the acknowledgements? Isn't about Docker acknowledgements. There's a ton of open source stuff in the acknowledgements. So I can just switch to a terminal. I'll just close this. OSS licenses. And if I just grep in there for some of the licenses, there's 74 licenses. And these are all OCaml libraries from the open source using the OPAM package manager. Now, there's some intriguing stuff in here. We can see things like there's DNS libraries, there's TCP/IP libraries, there's Fuse libraries, which is a file system format. There's all these OS X bindings. So you can see that pretty much the vast majority of the systems glue was built using OCaml. So I'll just give you a few examples of how that works now. But the nice thing about this is that using this kind of lightweight virtualization framework, we can just embed a Linux that effectively runs within a process. It doesn't require any extra privileges. And so we can just take a Linux distribution. We actually built one based on Alpine called Moby, which is extremely fast boots in less than a second, and it's completely stateless. So you can just run Docker info, and it gives you all that information. So this is the virtualization part of it. Now, virtualization is quite easy so far. So this was actually done in an offsite in the middle of France in about a week. So building the hypervisor was not a huge amount of effort. Running Linux was not a huge amount of effort. Where the effort begins is dealing with I/O, because dealing with the outside world is where virtualization is very, very complicated, because you want to do it fast, you want to do it low latency, and you need to figure out how to interact with the operating system. So how many of you have used Amazon, for example, in the cloud? Quite a lot of us. And the way that Zen works is that it modifies Linux with special protocols for dealing with I/O. But these protocols tend to require bridging and root access and so on. So we had to find a way to do I/O within this embedded app that did not require the kind of deep access to the operating system that for example, Zen requires, which Amazon runs. And some of the interesting side effects of a lot of this stuff is that when you build this kind of virtualization infrastructure, it's awesome for building desktop applications. So when you build a desktop application, you want to make sure that your performance is as if you're running the container on Linux. So because of the fact we're using hardware virtualization, if you run CPU tasks inside this thing, it runs at the same speed as if it's running in bare metal. It's only I/O is a little bit slower. Battery life, you're just running a normal application process. In fact, Docker for Mac uses up less battery than Safari. Because browsers are basically operating systems these days. And the disk usage is all managed internally. So all of this is kind of hidden away from the user. So we're trying to build in as much kind of self-healing logic in our functional programming smarts to make sure that users don't have to worry about this stuff. So the problem really began, and we deployed this so we released it to about, when we went to beta, we got about, I think it was about 35,000 signups in about 24 hours. So people really wanted this thing. And we just had this storm of pain from networking. Because the problem is, if you're in a data center, you control your networking. And you have a relative idea of what the topologies are and where everything sits and so on. But then you get to laptops, and the same developers who work for Jane Street or Morgan Stanley or any kind of institution with corporate IT realize that what's actually happening is that they're either in a coffee shop where there's some kind of Wi-Fi captcha. They're in a lockdown network here where they don't have unfettered access. And the way that networking is normally done is that when you write a virtual machine, you bridge the traffic from the virtual machine directly to the outside world. So if I'm running a Mac and then I'm running a Linux virtual machine, you just take the Ethernet frames from Linux and you just send them directly to the outside world. And it looks like there's two machines running there. That's kind of the point of virtualization, right? You just want a Linux machine to run. So here we had to undo the last 15 years of work in virtualization and say that, stop, we want this Linux machine that's hidden inside the application to be completely invisible. And the reason for that is because almost any kind of corporate installation of a machine does not want to suddenly see two machines running on your machine. They just want the policies they put in for one machine to be the thing that's running. So for example, VPN software used to kill Docker. Corporate installations with security policies kills Docker. And container traffic just cannot connect. So your developer who's trying to build software cannot do it. And similarly, because you're running a virtual machine, the fact that it's a separate networking IP address means that you can't just trivially expose it over your Mac's Wi-Fi. So if you're building something with a web flow, OAuth and stuff, it just wouldn't work. Because somewhere in there is a virtual machine with its own kind of network space. So we wanted to figure out how do you make this completely invisible. So the answer for this was to use a lot of the systems libraries that we built in OCaml. So there's a project called Mirage OS, which we started in Cambridge, which rebuilt all of the protocols required for an OS kernel in OCaml. So everything from low-level device drivers to TCP/IP to SSL to DHCP to DNS. And so over the last 6 years, we built up a really fun community of people who just go off and rebuild protocols using OCaml and functional paradigms. Everything is functorized and monadically concurrent and so on. So we had this huge hammer, and we were kind of looking for a problem, and the problem came along. And so the way that the Docker now works is that we reversed the normal flow of virtualization. So this container is running inside a Linux virtual machine, and we do a Docker run, so it starts operating and trying to connect to the network. And then we connect to, we have a Linux process, which has all the Ethernet, and we then inserted OCaml TCP/IP stacks to reconstruct this traffic and to build data structures representing the flows and on OS X, and then transform those TCP/IP flows into normal OS X socket calls. So normally you'd make an OS X socket call for get host by name or connect or read or write, and that would just go through the OS X kernel stack and connect to the outside world. Now this Linux virtual machine looks exactly like a native Mac app because we've reconstructed the traffic that is sent out to the outside world from NTP to DHCP, everything, and we've translated those into what the native Mac host does. So you can do a Docker run now, and it's indistinguishable from what Safari does or what Chrome does or any other Mac app. And it's done this by basically running the entire stack through a reconstruction library, which is written in a camel. So I can give you a really, the example is super non-dramatic because that's kind of the point. I can do, for example, a Docker run here. And if you're unfamiliar with Docker, I'm saying Docker run it interactively. And here I've got an OCaml container. I'm just running curl on my website. So I can do that. And this is running on my Mac, and it just connects to the outside world. So it's kind of a nice example of how functional programming was really good, because this took about a weekend to put together. So Dave Scott he took the final assemblage of libraries, but behind there was about 80 libraries to do all the TCP/IP and so on. But because they were just functional libraries, we could just embed them directly in the application as part of the process. So there's no systems level glue required. Hi.
So this sounds like the obvious approach to do this in retrospect. Are there any limitations with it? So is there something you're not telling us?
It's a really good question. I guess the question could be interpreted as what is the bug tail, right? Or if we'd use something that was non-functional, what is the cost going to be? So there's many user-level TCP/IP stacks. There's LWIP, there's the BSD ones. The problem is they're hard to extract from their context because normally TCP/IP stacks expect to be running in some kind of a systems context. They're hard to embed as independent libraries somewhere else. So what we do here is that depending on the level of the protocol, we cut off the stack. So we actually have a stack of functors that represent different levels of networking. So it could be HTTP, for example. So if you identify an HTTP traffic, we can just directly go to an HTTP library on OS X. So the ability to quickly chop and change and rearrange the libraries using OCaml modules was a key part of the architecture. Now it's hard to go into it in a 20-minute talk, but I can show you demos afterwards. Go ahead.
But is it less work than just implementing kernel system calls?
Yeah, that's a fantastic question. So you can implement the Linux system calls here, and we can do the translation. This is what Microsoft does in the Windows preview. But the problem is the OS X system calls are completely different. So OS X actually doesn't really have system calls that are in any way analogous to Linux. And much of the logic happens at the higher level. So name resolution, for example, it happens at the libc level. So you never even observe it inside a virtual machine. So there's some things where you want to know at a higher level what the protocol is. HTTP is a good example as well, because you want to know if you have a proxy, then you want to reconstruct it to the level of HTTP, and then use the OS X HTTP APIs, which are the NS Objective-C ones. So this way you get to use all of the local OS X function calls and so on to make that possible.
Sorry.
Go ahead. Yeah.
First, that's great. I've been using it, and it's just wonderful.
Oh, you've actually been using it?
Yeah.
Oh, great.
Well, my question was, how much of a shared code base do you have between the OS X hypervisor and Windows hyper-V?
We have the hypervisors, no code sharing at the moment, but we are working on unifying these things. So we've open sourced these as something called HyperKit. So what HyperKit does is that it's a kit that you can assemble into other applications designed to give you a homogeneous API across operating systems. So today we just have this big heavyweight Hyper-V running on Windows 10, but we're looking into adding more backends to HyperKit to basically support KVM directly on Linux, for example, and so on. But it's not there yet.
So the code for that app on Windows and OS X has nothing.
Oh, yeah, for the application there's no difference, right? Yeah, for the application there's absolutely no difference. So when you run a Docker for Windows or Mac, it's going through the same kind of reconstructed surgery, so there's no difference at all. So this is actually a big advantage because it'll eventually get translated into the Windows networking stack or Linux's networking stack, but we can intercept and homogenize stuff inside the VPN kit, which is this layer. So it's actually been quite successful because there's lots of subtle semantic differences in the way Windows does networking and Linux and OS X does networking. So we're smoothing those out inside our library and then injecting them to the outside world. And at the point of injection, there's lots of differences because it's the Windows networking stack, but that's okay. That's the point of the system. So it kind of works. There's also one other nice thing. So the benefits are basically, this now works. We hadn't had a single problem with VPNs and so on since then. So this is kind of a enterprise-ready bit of software. So if someone says that function programming isn't ready for the enterprise, we have over 100,000. We haven't even released yet. We've got over 100,000 users now, just using this sort of thing in a closed beta. There has been a tail of bugs, but the tail of bugs has been all fixable in a nice high-level way. And similarly, Docker has a mechanism where you can expose ports. So when you expose ports, the problem is you don't want to ever expose the internal virtual machine. You want to have a port listening to the outside world, but running on localhost. And we do this through the same style. We reconstruct a whole bunch of listeners and so on. We actually have a special address family in Linux because we modified all of these bits. And then we just have something in OS X that does a normal accept. So if I show you here a Docker exposed port, all that's happening here is I'm running an Nginx container. I'm mapping in my local file system, running Nginx, and I'm saying run it on port 8080 on my computer. So when I'm running this thing on the Mac, it's going through a virtual machine, but it just goes to localhost on my Mac, so it's indistinguishable from a normal. Oh, I put a photograph earlier. It didn't come in. Never mind. It's a pretty nice photograph. And it's running a localhost 8080, so it doesn't really look like there's a virtual machine there. So it does this by going through that reconstructive surgery. So I can even make this, we cheekily added in a privileged helper, so I can make this run on port 80 on my Mac, which would normally require root. And I can run it there. And at this point, the localhost should just work. So if you're building applications that require, you can do this without having root here because we have a tiny helper that basically mediates and makes sure that the port access is okay. But I've done all of this without requiring admin access to my Mac. So that's networking, and it's a good use of functional programming again because we've gone through the TCP/IP stack and we've able to massage everything and add policies. The real fun began with file systems. So if you think that there's differences in networking, file systems are just crazy. And the problem is that we're trying to just share two arbitrary things that have really undefined semantics. No one's really ever specified what POSIX means. And share them with a bunch of users who are using everything from NPM to Ruby to OCaml to Haskell to whatever language comes up to Rust, et cetera, Elixir to the JVM, and have it all just work. And every single one of these languages has spent decades being optimized down to the syscall level to take advantage of the specific semantics of the system they run on. So it was just a nightmare. And normally what happens is when I share something from OS X to the Mac using network file system, so things just don't work. So on the Mac, my default UID is 501 for a user. On Linux, it's typically 1000. And even things as simple as those kind of mappings cause permission problems to happen. So we built a new file system that forwards everything from the Mac, and again, written in OCaml, and it does a socket level translation. It tracks all the extra metadata required, for example, extended attributes and so on, and it translates into OS X file system calls. So once more, we make it look like it's coming from the native Mac app. So Apple just announced a new file system yesterday, a new Flash-specific one. In theory, we can translate everything to that one when we get our hands on it, and it should just work. And we can then, at this layer, take advantage of the OS X file system. And so we did this by building a new file system called OS X FS. And there was something interesting about it as well, which is the bidirectionality. So when you build a file system, you want to make the division between your host files and the container as invisible as possible. And it turns out that none of the other file systems ever supported notifications coming back. So if you make a change on the Mac, you want it to reflect using the notifications in the kernel, iNotify in Linux, and FS events in the Mac. So we made everything bidirectional as well. So everything could just go back and forth, and you'd use a native notification mechanism in the Mac and the native notification mechanism on Linux and have it just work. So I can just show you that really quickly. So if I look at Docker here, I am, at this point, just mounting my current file system into the container. Now I can look at my current file system. It's owned by AVSM. My UID is 501. And if I just run that, I'm now inside my container. And the thing I mounted looks at the current user ID, which is root inside there, and it remaps it dynamically. So all we did was just say, well, we're a bit of a chameleon. We'll just remap it and have it just work. So now permissions problems are a thing of the past, and it keeps track of changes and so on. You can also keep track of iNotify. So I'm also mounting my local file system in one terminal. So I'm now running a listener container. Now, if I just shift over to, if I just shift over, I'm now running on my Mac, I will say, hello, Jane Street. Hello. I will save that file. Now, I did this on my Mac. Inside the Linux container, we can see a real-time view of all of the iNotify events that happened there. So it went through this, this translation layer. Now, what we did for this was, this is actually years of work. We built something called SibleFS, which is a formal semantics of what it means to be POSIX. So this is a higher order logic representation written in something called lem, translated to OCaml, which gives us a precise executable semantics of POSIX across all allowable behaviors. There's full details in this paper called SibleFS. And it can do things like, for all obscure invocations of anything to do with a file system, for example, muctor or open, you won't believe how complicated open is. It works through all possible permutations and describes all allowable behaviors. So we finally kind of had an idea of what you can do for each single one with traces and so on. So you can look at a particular structure, run a series of traces, for example, stat, know that if you muctor with this flag, the spec permits one thing and you can't do anything else. So this kind of higher order logic representation, also written in an extremely functional style, gave us enough semantic clues to be able to build this kind of new translation layer for the Mac. So we've now successfully, we think, I don't think anyone's ever shipped something quite like this. We can essentially do OS translation at the library layer and translate precisely the POSIX from Linux into the POSIX for OS X. And I use POSIX very loosely here. There's all kinds of breakages on both sides, and we can fix those up and massage those inside this OS XFS. So I won't go into the details here. We haven't open sourced this yet. We've open sourced the VPN stuff, but we will open source this as soon as it's ready and we're out of beta. And there's tons of nice features and stuff. So I'm just going to close up now. I just want to give you one last Easter egg as well. When you do virtualization, you can also make it multi-CPU. So when you're on the Mac, we can run Windows and Linux and stuff. It's also possible to run ARM binaries. So if you're into Raspberry Pis, I'd encourage you to download the Docker for Mac, because I can build a little file system using a normal Docker on this setup, except if I look at uname here, it's actually running an ARM v7, and I can file user SBIN file, for example, and it's a full ARM v7 executable. So you can, for the first time, I can just run OCaml, I'm not running OCaml in this container, but I can apt-get install it, and it will be the native OCaml. So we can now build Raspberry Pi applications, for example, straight from Docker for Mac, using all of the volume sharing and the Docker Hub pulling and pushing, or indeed, if you're into PowerPC 64, you can use that as well. Pretty much any architecture available. Sorry.
You have QEMU in there, right?
There's QEMUs in there doing the emulation, but only for the ARM or PowerPC. So, and where possible, it uses native. So in theory, if we ported this to ARM, it would just use native. So we shim in a little emulation there over there. So it is quite slow, but ARM is luckily quite slow. So it's good enough for Raspberry Pi. So a lot of this stuff is open source. I wanted to encourage anyone who wants to get into systems programming and also into functional programming. Virtualization is a really exciting area right now. There's tons and tons of open source activity. So there's Docker itself. We have something called the HyperKit, which is our new layer, the VPN kit, which is all of the networking translation. You go to Mirage.io, which is the overall project for unikernels and OCaml, and DataKit, which is a coordination layer that we use to keep all these things together using a Git-like database. If you do want to get into it, then we have all these hackathons coming up. So we have a Mirage OS hackathon in mid-July in Cambridge. A lot of these happen in Cambridge in the very comfortable confines of Pembroke College. And we have compiler hacking sessions every month or so we're going to have one sometime in August. And Gemma Gordon, who is here, is, where's Gemma? She's hiding in the back right there. So you want to grab her and ask her about attending these things. But beginners and people just curious are more than welcome if you can tolerate the 45-minute train ride up to Cambridge from here. So thank you very much for your time. This is a bit of a whirlwind tour. Hope that was useful.